Have you ever trained a machine learning model that looked absolutely perfect on paper, just flawless, only to watch it completely fall apart in the real world? Well, the problem might not have been your model at all. It might have been a really subtle but powerful statistical trap called the winner's curse, a bias that can trick you into thinking your results are way, way better than they actually are.
Okay, let's get right into it. Here's our game plan. We're going to start with a core mathematical idea called Jensen's inequality. From there, we'll see how that single concept creates this bias when we pick the best model, and how that leads to something called the winner's curse. And most importantly, we're going to talk about how to actually fix it. All right, so to really understand the winner's curse, we first have to build a solid foundation. And that foundation is a mathematical rule that, believe it or not, powers this whole phenomenon.
This might look a little intimidating, but stick with me. This is Jensen's inequality. And all it's saying is that for any convex function, and you can just picture a curve that's shaped like a bowl or a U, the expectation or the average of the function's outputs is always going to be greater than or equal to the function of the average input. Let's break that down into plain English. Imagine you've got a set of numbers. If you run each number through that bowl-shaped function first and then take the average of all those results, you'll get a bigger number than if you did it the other way around, averaging the numbers first and then running that single average through the function. This tiny little mathematical quirk has massive consequences.
And here's the thing. This rule doesn't just work for single numbers. It works for vectors, for whole lists of numbers, too. And that is so important because in machine learning, we're pretty much always dealing with multiple things at once. Multiple models, multiple features, you name it. And that's exactly where this bias starts to sneak in.
So you might be wondering, okay, what does a bowl-shaped function have to do with my day-to-day work? Well, what if I told you that one of the most common things we do is itself a convex function? And that's the simple act of picking the maximum value. Yep, it turns out that mathematically, the max function, literally just picking the biggest number out of a set, is convex, which means that every single time you look at a leaderboard of models and select the best one, you are applying a convex function. And the second you do that, Jensen's inequality kicks in. And this formula right here, this is the smoking gun. It shows us the core of the problem. When you pick the maximum score from a set of models, the expected value of that winner is going to be higher than the true best score of their individual average performances. In other words, you're not picking the best model. You're systematically picking the luckiest one. And this is the part that really blows people's minds. Even if every single one of your models, on its own, gives you a perfectly fair, unbiased estimate of its performance, the very act of selecting the best one introduces a brand new optimistic bias. The moment you declare a winner, your estimate of that winner's skill is probably too high. Now, this isn't just some weird machine learning quirk. This statistical phenomenon is so well known, it has a famous name and a classic real-world example that has nothing to do with computers. I want you to picture an auction for, say, an oil field. Nobody knows for sure how much oil is down there, so every company makes its best, unbiased guess. So, who wins the auction? Well, the company that bids the highest, right? But think about it. The highest bidder is very often the one who, just by random chance, overestimated the value the most. They win, but they've likely overpaid. That's the winner's curse. This amazing comic from XKCD shows the exact same problem, but in the world of scientific research. So imagine you're a scientist, and you decide to test if different colored jelly beans cause acne. You're testing a whole bunch of hypotheses at once. So you run 20 different tests, one for each color. For 19 of them, nothing, no link. But if you're using that standard p-value of 0.05, that means you'd expect to see a false positive about 1 in 20 times, just by pure random luck. And lo and behold, the green jelly bean test comes back positive. It's our statistical winner. And the curse happens right here, when you only report that one positive result. You've selected the winner from all your experiments, you've ignored the 19 failures, and you rush to publish a headline that is completely and utterly misleading. You didn't find a real effect, you just found a fluke. Okay, so we've seen this in auctions, we've seen it with jelly beans. Now let's bring it all back home and see how this exact same problem is baked right into the way we build and evaluate our machine learning algorithms. See, at their heart, most learning algorithms are what we can call utility maximizers.
Their entire job is to hunt through a sometimes astronomically huge space of possible models or hypotheses and find the single one that gets the highest score on the training data you gave it. They are literally designed to find the winner.
Take a look at this. This is what a one nearest neighbor algorithm does. It's kind of an extreme example, but it's like the ultimate memorizer. It can create this incredibly complex, jagged boundary that perfectly ropes off every single data point in the training set. It will almost always get a perfect score on the data it trained on. And this ability to perfectly memorize leads to a very tempting but deeply flawed way of checking your work. It's called the Resubstitution Estimator, and it's when you test your model's performance on the exact same data you used to train it. And here's the trap. This creates a critical dependency. The algorithm's entire purpose was to find the one hypothesis that works best for that specific data set. So asking it how well it did on that same data is like asking the scientist to rerun only the green jelly bean test. Of course it's going to look amazing. It's a completely biased, wildly optimistic estimate. So if testing on our training data is a huge no-no that gives us these inflated, biased results, what are we supposed to do? How do we get an honest look at our model's performance? Well, the answer is actually really simple, but it's incredibly powerful. It's called the holdout principle.
The solution is just to split our data. It's that simple. Instead of using the same data for both training and testing, we carve out one chunk for training and a completely separate, untouched chunk just for testing. This one little change makes all the difference in the world. So here's how it works. We let the algorithm do its thing. We let it search and find its winner, the absolute best model it can find, using only the training data. But then, to see how good it really is, we evaluate its performance on the test data, which it has never, ever seen before. This breaks that dependency and completely avoids the winner's curse.
This holdout method gives us a much more honest, much more realistic estimate of how our model is going to perform out there in the wild. It is the absolute bedrock of modern machine learning evaluation, and it forms the basis for even more robust methods like cross-validation, which is really just doing this holdout process over and over again and averaging the results. So the next time you're looking at a leaderboard of models or you see one with an absolutely incredible performance score, just ask yourself, was its performance evaluated on truly unseen data? Or are you just looking at the lucky winner of a hidden lottery, cursed to disappoint the second it faces the real world?